Okay, welcome back everyone. We are going to wrap up our discussion of the law of gravity by looking at a very special case of gravity, and that's black holes. So we're going to be looking at just a couple things. This is because black holes are really cool and interesting to think about, but what are their properties and how do they form? So to understand black holes, we have to go back to the concept of escape velocity. So remember that this was the square root of 2gm over r. Well, it turns out that there is a speed limit in the universe, and the fastest that an object can travel is the speed of light, so 300 million meters per second. So what we can do is we can rearrange the escape velocity equation to solve this for r. So, in other words, r would be equal to 2gm over v escape squared. But it turns out that because the upper limit for the escape velocity is the speed of light, we get something that looks kind of like this. R is equal to 2gm over c squared. So this particular value of r, rs, is called the Schwarzschild Radius, and it tells us the size of an object with a mass of m that's so gravitationally strong that not even light can escape from it. Okay, so this event horizon is called the Schwarzschild Radius. And when the radius of an object is bigger than the Schwarzschild Radius, so in this case r is bigger than rs, light can escape. Okay, but what happens is that gravity acts on the escaping light and it becomes redshifted to longer wavelengths. In essence, the light is losing energy as it climbs out of the potential energy well. Remember that as you move away from an object, your potential energy decreases. Now, light doesn't really have potential energy, but it does have energy in the form of a constant, Planck's constant, times its frequency. So the frequency will become less as the energy goes down. And when that happens, the wavelength goes up, and this is what we call redshift. However, if all the mass of the object is inside the Schwarzschild radius, that's when you get a black hole. And in that case, no light can escape from it whatsoever. So, as a very quick practice problem, let's think about this. How small would you need to compress the Earth to turn it into a black hole? So, Rs is 2gm over c squared. And so g is 6.67 times 10 to the minus 11th. M, this is the mass of the Earth, is about 5.98 times 10 to the 24th, and that's in kilograms. And then the speed of light is 3 times 10 to the 8th meters per second, and that is squared. Okay, so when you do this, you get 0.0089 meters, which means that if you could take the entire Earth and squish it into something that was approximately 1 centimeter in radius, like a large marble, then it would have enough gravity to create a black hole. Okay, so there's lots of other things that we could talk about with black holes. One thing that we could talk about are their physical properties. And it turns out that really the only things that you can discern about a black hole is the mass, the charge, and the angular momentum. So we haven't really talked about charge too much yet in mechanics, but it's a property that's similar to mass that describes how the black hole interacts electrically with its surroundings. And we did talk about angular momentum. Now, one weird thing that happened earlier last year is it was announced that two black holes coalesced and they were orbiting each other, and when they coalesced, basically they became intertwined by each other's warping of space-time, and they gave off gravitational waves. So that was kind of cool. Okay, so we're going to stop here, and this is the end of our unit on gravity. And next time, we're going to start our last unit in mechanics, which is periodic motion.